Okay, the first part of section 5.2 is talking about central angles, and it's imperative that we understand how to find, how to use a central angle and find the arc length um, of an arc, because we are going to be moving into what's called angular velocity, and we're going to do a project with angular velocity involving a pitching machine. It's actually a really neat project, and I think you guys enjoy it, but it's very imperative that we understand what a central angle is and how we use that central angle to find the length of an arc. And so I'm going to go ahead and explain. Well, you might be thinking, well, what is a central angle? Central angle is the angle whose vertex lies at the center of a circle. Okay, so we've talked about the unit circle right now, and obviously this is a horrific drawing of the unit circle, but it's going to have to do for now. And when we're talking about a central angle, we're talking about the angle an angle that is formed in the middle of the triangle or the center of the triangle. This right here is its central angle. Okay, so it says if two central angles in different circles are congruent, the ratio of the lengths of their intercepted arcs is equal to the ratio of their measures of the radii. So we can set up a ratio comparing arc length and saying that the ratio of their lengths, their intercepted arcs, so arc length all over the radius, or radii, or radius, would equal the other circle's arc length all over the radius as well. So that's saying that it's a ratio and it's a proportion. Okay, so we know what a central angle is, and what we're going to talk about now is the length of an arc. The length of any arc, circular arc, S, is equal to the product of the measure of the radius of a circle and the radian measure of the central angle theta that subtends. By the way, subtends means that that these two rays, these are subtending the circle. It means they are going through the circle. They're passing through the circle, and this is the arc that now that is formed out of these, that is formed from these two, from this angle. All right, and so let me explain the formula of arc length and why it's important that it's in radian measures. If you notice, there's a nice little keyword in here that I put in a PS is, remember theta is in radians. And if you remember what we talked about, the difference between radians and degree measure is that the radian was dealing with the unit circle, and it was actually dealing with the arc length. Okay, so it's telling us the arc length at a given angle. So it was telling us this arc length, and this thing had a radius of 1. Okay, so to make this make sense, if this theta is the arc length with the radius of 1, the unit circle, in order to tell all other circles, because not all circles have to have a radius of 1, they might have a radius of 5 or whatever. Maybe I have a bigger circle, and now I want to know if this is the same angle. Say both of these angles were 30 degrees. Well, obviously you can see that this arc length is going to have to be smaller than this arc length because it's a bigger circle. It has more distance between these 2 points. And that's because the radius is bigger. And you know that radius ties into circumference because circumference is 2 pi r, right? That's how we find the circumference of a circle. And the circumference of a circle is a distance around the circle. Okay? So since this radius is bigger, we're going to have to multiply by now what the radius is. So a typical radian measure was just this arc length when it had a radius of 1. And now when we're changing circles, because we can have bigger circles, we're going to have to change what our arc length, or what our radian means, and it's going to mean an arc length of a bigger circle. And we're just going to take it times this new radius. Okay, so I hope that made sense to you into why or where we came up with the arc length formula, and it all revolves around your understanding what a radian measure is. And a radian measure is based on the arc length of an angle measure, okay, in a unit circle. So a unit circle where the radius is 1, all right? And so we don't always have to have a circle with a radius of 1. Say this is a radius of 5. This is going to have a different distance around here, so this distance is going to be different. And it turns out it's going to be different in the sense where we're just going to multiply it by 5 compared to what this was. Okay? So that's all really our new lesson is about. And I'm going to show you an example of how to find the arc length with a central angle of different degrees. So it says find the arc length that subtends a central angle. So all we know that it means we have a circle, okay? And we have 2 rays here, is what it said. And it said this is 42 degrees. And they want us to find its arc length. And it has a radius of 8 centimeters. And this 8 centimeter radius is bigger than our typical 1 centimeter radius. So we can find the arc length of the unit circle when it has 42 degrees simply by just finding the radian measure. So we need to convert 42 degrees to radian measures. And remember how we did that? We had our conversion formula where we need degrees to cancel out. So pi must be on top. And so now my degrees are going to cancel out, and now I'll have a radian measure. All right, and we know we can both take, we can take 2 out of each of these guys. I suppose we have 21, and we have 90. Well, I know a 3 comes out of these. This would be 7, and this would be 30, and I think that's all we can take out of it. So now we multiply straight across, and my radian measure is now 7 pi over 30, multiplying straight across. That's my radian measure. That's 42 degrees in radians. All right, that's the distance of this arc had this been a unit circle. Had this had a radius of 1. Well, now it has a radius of 8. So our formula says arc length equals S equals R times theta, where theta is in radians. So we already know that theta, the measure of theta in radians is 7 pi over 30, and we're going to take it times this new radius because we have a circle bigger than 1. So arc length equals 8 times 7 pi over 30. Okay, so to find our arc length, we can cancel out again. We're multiplying fractions. We can take a 2 out of both those, and this is 15, and this is 4. And so we would get 28 pi all over 15. And so that now is our new measure of this arc length. And if you actually wanted to know the exact measure as far as centimeters, you could take 28 times pi, and then you can divide by 15, and you have it's roughly 5.86 centimeters is that arc measure there. Okay, so let's do one more example. Find the length of an arc that subtends a central angle of 38 degrees and with a circle with a radius of 5. So it's going to be the same type of circle. You might want to pause this and try it yourself, and I'm obviously going to work through the answer here, but you might want to try this, see if you get the right answer, and then you can go ahead and watch, and I'll show you here. So now I'm going to go ahead and I have a circle here. Well, that wasn't a very good circle. I was going to draw the x-axis, x and y-axis, but we don't need it. So I have a circle, and we have a central angle of 38 degrees. Okay, in order to find my arc length, S equals R theta, and theta had to be in radians, and we're given degrees, so the first thing we're going to have to do is we're going to have to convert degrees to radians. So 38 degrees, and my conversion chart says I need to choose from either pi over 180 or 180 over pi. Well, we need to choose, we need to get to radians, so we need the degrees to cancel out, so we need degrees on bottom. So pi over 180, so now my degrees cancel out. And let's simplify this thing. Again, I can take a 2 out of that and be left with 19 and 90. And I think that's all the farther I can reduce. So then we multiply straight across. So my theta is now 19 pi all over 90. And my radius is 5, we know. They gave us that in the problem. Equals S. All right, and again, we just multiply and we'll look diagonal first, so we make sure we're in simplest terms. I know I can take a 5 out of 90 because it ends in a 0, and it's going to be 18. And this is a 1, so now when I multiply straight across, it is 1 times 19 pi, which is just 19 pi all over 18. And if we actually wanted to know the actual number, we could take 19 times pi and divide by 18. And we'd get, it's approximately 3.316, what is this? 5, what? It doesn't say. We'll just call it centimeters. So this arc length here is roughly 3.16 centimeters. Okay? Hope that makes sense to you, and I hope I explained why we have an arc length formula the way we have it, and I hope it makes sense to you, and I hope it gives you a better understanding of what a radian is and why we have to use radians when it comes down to finding the length of certain things, because a radian measures length. Degree is not length, okay? A radian measure deals with length. So anytime we're finding the length of something, our degree or our measures of our angles has to be in radians, okay? Hope this helps. We'll see you in class.